Welcome back. In this section, we're going to start looking at a new function called a logarithm. What a logarithm is just the inverse of an exponential function. And before we start talking about that, I think let's have a moment just to recall a couple of things about inverse functions. So one of them was that for inverse functions, what they do is they switch the inputs and the outputs. So for example, we know the function, the cubing function and the cube rooting function, that those are inverses of each other. And for example, if we were to take something like 5 cubed, we would get 125. But if we wanted to think about the equivalent statement in terms of the cube rooting function, we would switch our inputs and our outputs. We would have the cube root of, instead of 125 being the output, 125 would be the input. And instead of 5 being the input for our function, 5 would be what comes out of our cube rooting function. So that was one of the key ideas for inverses, that inverse functions are just switching the inputs and the outputs. The other idea, of course, that we had was for an inverse function to exist, you needed that function to be one-to-one. And that was the reason why we knew y equals x cubed had an inverse, and that was because the graph of y equals x cubed passes the horizontal line test. Any horizontal line grows through the graph of y equals x cubed no more than once. So let's think about what we just learned in 6.2. So in 6.2, we looked at the graphs of exponential functions, and for any exponential function, there was a horizontal asymptote, and then it had one of two shapes depending on whether it was an increasing function or a decreasing one. But either way, the exponential function is a one-to-one function. It passes the horizontal line test, which means the exponential function should have an inverse. For every exponential function with that whatever base we have, we're going to have an inverse with the same base. So if we're talking about an exponential function with base a, then the inverse of that would be a logarithm with base a. So that means we don't just have one logarithm, we have every kind of logarithm for every kind of base we might have. So if you had a function that was 3 to the power of x, its inverse would be log base 3 of x. And if you had a function that was 7 to the power of x, then the inverse would be log base 7 of x. So for this function, the log base 7, that's the name of our function. I'm not doing anything with the 7 and the x. I'm not combining them in any sort of a way. Log base 7 is just the name that I have for my function. And the same thing is true as before, the switching of the inputs and the outputs. If we knew that 5 cubed was 125, that's an exponential function with base 5. So its inverse should be a log function with base 5. And you'll notice what we've done is we've again switched the inputs and the outputs. For the exponential function, 3 was the input. For the logarithm, 3 becomes the output. For the exponential function, 125 was what came out of it. So for the logarithm, 125 is what goes into it. One other thing just to sort of remind ourselves of, for exponential functions, we restricted what kind of bases we could have. The base had to be something positive, and also the base couldn't be 1. So for exponential functions, your base was either between 0 and 1, or your base was larger than 1, and that was it. And since those are the only exponential functions we're interested in, then for logarithms, it's going to be the same. For them, the base would have to be something positive, and you would also need the base to not be 1. So there would be no such thing as log base negative 2 of x, that's not a thing, or log base 0 of x, that's also not a thing. So for any number that we might have, for a possible base, it would have to be something strictly positive, so bigger than 0, and it also couldn't be 1. So now let's do a little bit of work going back and forth, rewriting statements as logarithms or taking logarithms and rewriting them as exponential statements. For this first one, we've got 3 to the power of 4 equals 81, and I know that that's an exponential function with base 3. So as a logarithm, it should be log with base 3. And again, we're going to just switch our inputs and our outputs. So instead of 4 being the input, 4 becomes the output. Instead of 81 being the output, 81 is the input. Next one up, we've got a logarithm this time, and it's log base 2 of 16 is equal to 4. So if we're thinking about rewriting this as an exponential statement, since it's log base 2, it would have to be an exponential statement with base 2. And again, we're switching our inputs and our outputs. 4 was the output for the logarithm, so 4 is the input for my exponential function. It becomes 2 to the power of 4. And instead of 16 being the input, 16 becomes our output. This kind of brings something to mind here as far as interpreting a logarithm. So if we're wondering, how do we interpret what does log base 2 of 16 mean, or what does log base 3 of 81 mean? When I say log base 2 of 16, I'm asking 2 to what power gives me 16, and the answer is the power must be 4. Or when I say log base 3 of 81, what's that? I'm asking 3 to what power gives you 81, which is also 4. Or in the previous one, when we had log base 5 of 125, I'm asking 5 to what power is 125? And the answer is the power is 3. So for the exponential function, we know what the power is, and we're finding out what is the base to that power. With a logarithm, we know what the base to the power is equal to. We want to know what was the power. Now, where this becomes kind of useful to us is for things like this, 3 to the power of x minus 1 equals 7, or the log base 5 of 3 minus x equals 2. If you are interested in trying to solve for x for either of these two equations, you run into a problem right away. And the problem is, in the first one, x is a power, so how are we going to get x to no longer be a power? Or for the second one, x is a number that's going to be going inside of a logarithm, so how do we get the x to no longer be going inside of a logarithm? And the answer is we're just going to do the business that we did on the previous slide. Taking this exponential equation and rewriting it as a logarithmic equation is going to take x from being a power to x no longer being a power. Or for the logarithmic function, if we rewrite it as exponential, instead of 3 minus x being something going into a log, 3 minus x will be the output for an exponential statement. So for this first one, 3 to the x minus 1 equals 7. Since it's base 3 for my exponential function, it should be log base 3. And again, we're switching our inputs and our outputs. 7 is what's going into my logarithm, and x minus 1 is what's coming out. And so now if I felt like solving for x, I could. All I'd have to do is move the 1 to the other side, and I'd have solved my equation for x. Same sort of thing with the next one. Log base 5 of 3 minus x equals 2. If I wanted to try to solve for x for this kind of an equation, I'd need x to no longer be the input for a logarithm. So I would say, well, since this is a log with base 5, I'll rewrite it as exponential with base 5, swapping our inputs and our outputs. And then same thing as with the previous one, where I could now solve for x if I wanted to. Here I could also solve for x if I wanted to, just evaluating 5 squared and moving the 3 over and just doing that sort of business. One little bit of notation just to notice, so sometimes I'm using brackets with the logarithms, sometimes I'm not. If it's logarithm of just one single number, we don't really need to put brackets around it to indicate what's going inside that log. So if I write log base 3 of 7, I could put brackets around the 7 if I want to, or not. But for something like log base 5 of 3 minus x, where I have a two-term expression going into my logarithm, I really do need brackets there, because if you just wrote log base 5, 3 minus x, I would interpret this without brackets as being 3 is the only thing going inside the logarithm, and that this x is a separate term altogether. So we will have to be a little bit cautious when it comes to using brackets. And so if our input is more than one term, then we'll definitely want to be using brackets for our logarithm. Now, there's still a couple of other things to think about here. I also mentioned with this first one that if we wanted to solve it, we could, and we could bring the 1 to the other side, and we'd have solved for x. But then that doesn't address the question of how do we figure out what log base 3 of 7 is as a number? Because that's 3 to what power gives us 7, and the answer is it's not going to be a nice number because 7 isn't a nice even power of 3. It's not a 3 squared or a 3 cubed or a 3 to some nice number. It'll be 3 to some horrible decimal number gives us 7. So how will we evaluate that? It's going to take us a little while to get to that point. So we'll actually be able to get to this in a couple of sections from now when we look at coming up with decimal values for all of our logarithms. But for right now, let's just continue on doing some more work with logs. A couple of little things just to mention, and this is other little bits of notation that are important. And I've said this before, but worth repeating it, that when I say something like log base 2 or log base 5, that's the name of our function. We're not doing anything with the 2 and the 8. They're not being combined together in any way, or the 5 and the 8. They're not being combined together in any way. And that's a frequent source of misunderstanding for a lot of students. When they look at something like log base 2 of 8, they imagine that they need to multiply the 2 and the 8 together, or add them together, or do some arithmetic involving 2's and 8's. And the answer is no, you don't have to do any arithmetic involving 2's and 8's. If you wanted to know what log base 2 of 8 is, you'd be asking 2 to what power gives you 8? The answer would be 3. But other than that, you're not doing any sort of work combining these two things together. They're not able to be separated from each other in any way. That means there's a lot of things that are not possible as far as simplifying or canceling that a lot of people wish would be possible. For example, a lot of folks would look at something like log base 2 over 8 and log base 2 over 7, log base 2 of 7, and imagine that you could somehow cancel the log base 2's and just be left with 8/7. And that would be completely wrong, because it would be the same reason why you couldn't, with a function, take f of 8 and divide it by f of 7 and say we're going to cancel the f's and be left with 8/7. In the same way, you couldn't cancel the f's because that's the name of the function. We can't cancel the name of the function. Here, log base 2 is the name of the function. We can't cancel it for the same reason. So too bad for that. Same sort of thing where we have other sort of attempts at simplifying or canceling, where people might say something like log base 2 of 8 divided by 8. They might say, I'll cancel the 8 with the 8. And that also is completely not correct, for the same reason that if you had f of 8 for some function and then divided that by 8, you wouldn't be able to cancel the 8's there and say that that's f of nothing divided by 1. That wouldn't make any sense whatsoever. So same sort of thing here. You wouldn't be able to cancel the 8's because 1 is just a number on its own and 1 is a number that's going into a function. Similarly, this 8 in the denominator is just a number on its own, whereas the 8 in the numerator is one that's going inside of a logarithm. So there's lots of things where it might look on the surface where you might be able to cancel them, like you might be able to cancel the word log with the word log, which you cannot, or cancel this 8 with the other 8, which you also cannot. So we need to be careful here and always keep in mind that when we say log base whatever, that's the name of the function. And just like we had when we were doing stuff with functions in chapter 3, we can't cancel the f's and the g's for f of x and g of x. Those are just the name of the function. It's there for that reason. We're going to see the same sort of thing, by the way, coming up later on in chapter 7 when we look at trigonometry, where for similar reasons, something like sine of 45 degrees divided by cosine of 45 degrees, you wouldn't be able to cancel the degrees because, again, that would be the name of the function, and 45 degrees is the number going into that function. So that's kind of a running theme through this course, through the next couple of sections. We have some new functions whose name is not just a letter f or g. In this case, logarithm is a function whose name is, in this case, log base 5 or log base 2. Or later on in trigonometry, our functions will be named sine or cosine or tangent. Okay, so while we can't evaluate every single log by hand, for some nice ones we might be able to. So for these ones, all of the examples that we're looking at here, we can answer what is log base 3 of 9 by asking ourselves the question, 3 to what power gives us 9? Or log base 2 of 1/8 by asking ourselves the question, 2 to what power gives us 1/8? So let's get started here with this first one. If we're looking for log base 3 of 9, we're asking ourselves 3 to what power gives us 9? And the answer is the power is 2. And so that's my answer to how I know log base 3 of 9 is 2, and that's because 3 squared is 9. Or similarly, if I'm looking for log base 2 of 18, log base 2 of 1/8, I know that 2 to the power of -3 is 1/8, which means log base 2 of 1/8 is -3. Or for the next, if we ask log base 7 of 1, 7 to what power gives us 1? And the answer is the power would be 0. Anything to the power of 0 would be 1. So actually, that gets us another little side consequence that we can use going forward. I just said a moment ago that anything to the power of 0 is 1. So in other words, any base a to the 0 is 1, which means log of any base of 1 must be 0. So this is actually a nice little fact about every single logarithm. So if this had been log base 8 of 1, the answer would be 0. Or if it had been log base 12 of 1, the answer would also be 0. Or log base a half of 1, the answer would be 0. Because in all those cases, whatever the base is, raised to the power of 0 gives us 1. Next one up, we're looking at log base 15 of 15. So we ask ourselves, 15 to what power gives us 15? Or in other words, we know 15 to the power of 1 is what gives us 15. So 1 should be the output of that logarithm. The other thing we might notice is this would be true for any other pair of matching numbers. Like if you'd had 14 to the power of 1, that would be 14, or 15 to the power of 1 is 15, or 3 to the power of 1 is 3. So in general, a to the power of 1 is a, which means that log base a of a would have to be 1. So that's another little fact that we have about logarithms. We've actually just figured out two nice little properties. For any base, log base a of 1 will always be 0, and for any valid base, log base a of a will always be equal to 1. The next one up, last two to do, we have log base 2 of 2 to the 5. This one, we're asking ourselves the question, 2 to what power gives us 2 to the power of 5? And so just sort of repeating it again to yourself, 2 to what power gives you 2 to the power of 5? The answer is 5. It's 2 to the power of 5 that gets me 2 to the power of 5. So what should my output be? It should be 5. And of course, we could imagine doing other powers as well. If I'd said log base 2 of 2 to the 6, the answer would be 6, because 2 to the 6 is 2 to the 6. Or if it was log base 2 of 2 to the anything, it would be that anything, because whatever power we were given, it's 2 to that power. Sometimes we'll also be able to evaluate a log if we're just thinking a little bit carefully about what we know about exponents. This last one, we've got log base 2 of square root of 2, but if we remember that square root is really a power, if we remember that root of 2 is really 2 to the half, then we've got actually an easier question. 2 to what power gives us 2 to the half? And the answer is 1/2. Okay, let's do a little bit of solving of equations here. So we're going to do a lot more later on. In 6.6, that's really where we focus on solving equations. But at least now with what we know about inputs and outputs being switched, we can go ahead and come up with some solutions to these problems. So let's start with this first one, where we've got log base x of 36 is equal to 2. So we're looking at this problem and we need to solve for x, and here x is the base. and it's the base of a logarithm. So unfortunately, there's no way to just start shuffling things from one side of the equation to the other and get rid of the x and move it somewhere else. It's attached to that log currently. The only way to make it no longer attached to that logarithm would be for us to take this equation and rewrite it as something exponential. So let's do that. For this logarithm, the base is x. So as an exponential function, the base would also be x. And we'd be swapping out our inputs and our outputs. So I've taken that equation, log base x of 36 is equal to 2, and I'm now getting the equation out of this that x squared must be equal to 36. And now I just need to solve for x, and that's not hard for me to do. I'm just going to take a square root, and of course when I do, it's plus or minus square root. So I come up with two potential solutions. One of them is positive 6. One of them is negative 6. So here's where we need to remind ourselves of one thing, and that is for a logarithm, the base has to be something positive. So I actually need to make a little note here that I need to reject x being negative 6 because the base for any logarithm needs to be greater than 0. So really the only solution that I have for what is a valid base that will make that equation a true statement would be just 6. So 6 is the solution to that equation. Okay, a little bit of notation here. We've got two special kinds of logarithms, and that's because there's a couple of cases in life where we have some pretty common bases that are being used. In terms of exponential stuff, base 10 is really common. If you're thinking about our old friend, the metric system, that's all based on base 10. You have meters, which is 1 meter. You have kilometers, which is 10 to the power of 3 meters. You have millimeters, which is 10 to the power of negative 3 millimeters. All of those units we have for metric are really powers of 10. And so for an inverse, we'd have log with base 10. Another place where we have a common number that shows up fairly frequently is a base e. As we saw in 6.1, that exponential function with base e, that shows up in some applications. We had it showing up in finance, but we'll also see later on it shows up in some biological applications and chemistry as well. And so e is a pretty common base as well. So the two little notations that we have would be that if we're talking about log base 10, often we'll just dispense with writing the log and write it as log x, and it's understood that the base for this should be 10. Similarly, instead of writing log base e, often we'll write it as ln, so that's the natural log of x. Natural log because we call e the natural number. Log base 10, we call that the common logarithm. Most calculators, they come with two buttons built in, one of them to evaluate a log base 10 and one of them to evaluate a log base e. If we just take a look at our calculator for a moment, we have our two buttons for the logarithm right there, the log base 10 button and the natural log button. So that's why we kind of had to talk about notation first, because a lot of times students will look at this button and imagine that this is an all-purpose button that can be used for logs of every single base, and the answer is no. Specifically, this button is a button for log base 10. And you'll notice that as a second function, it's paired with 10 to the power of x. Just in the same way how natural log is paired with its inverse, e to the power of x. To use these buttons, it's pretty easy. We just touch log and then whatever we're looking for log of. So if you were looking for log base 10 of 7, you would enter log and then 7 and then equals. Of course, these things that we're going to evaluate are certainly not going to be nice numbers, because if we're asking ourselves, what is natural log of 3, we're asking ourselves e to what power gives us 3, and the answer is not going to be anything terribly nice. It's going to be some sort of terrible decimal number that we're going to have to round off, and in this case, it turns out to be about 1.0986, so if I'm rounding it to 3 decimal places, 1.099. And the next one, log 7, so this is log base 10 of 7. We're interested in 10 to what power gives us 7. Again, it's not going to be a nice number, but we can calculate anyhow and find that 10 to the log base 10 of 7 should be about 0.845. So what this is telling me is that e to the power of 1.099 should be about 3, and that 10 to the power of 0.845 is about 7. Again, this still leaves a couple of things to figure out. So we can now find log base 10 of things and log base e of things. But for other logs, like the ones that we might be interested in, like log base 5 or log base 3, we're going to need some extra theorems to help us out with those. So we're just going to keep in mind that there is still more to learn about evaluating logs. But for now, that's a good little start for us. Let's do a little bit more solving of equations. While we're here, do a couple little moments. And you'll notice the running theme through all of this is that if we have an exponential equation and we want to solve it, a lot of times a good way to do that is to rewrite it as a log. Or if we have a log equation and we want to solve it, a good way to do that is rewrite it as something exponential. So for this first one, we see log x equals 5. And for this, we're going to understand that when we say log x, we really mean log base 10 of x equals to 5. So if I wanted to rewrite this as an exponential equation, it would be with base 10, switching our inputs and our outputs. So that x would be 10 to the power of 5, or x is 100,000. And same thing with natural log of x equaling 0. We remember that natural log of x is the same thing as log base e of x. So if we wanted to rewrite this as an exponential equation, it would be with base e. E to the power of 0 equals x, or in other words, x is 1. A little bit more to do, a couple more ones for fun. Log x equals 1. So again, we're noticing that this is log with no base written in it, so that's understood to be log base 10. That means as an exponential function, we'll rewrite it with base 10, switching our inputs and our outputs, so that x is just 10. Similarly, natural log of x equals 1, that's a log base e. So as an exponential function, we'll make it with base e, switching our inputs and our outputs, so that x is just e to the 1, or x is e. Okay, so a couple little last questions to do, and this is sort of flashback to section 3.7, where I've given us a function and I want us to find the inverse of a function. So a couple of things first. How I know that this function should have an inverse is because I know that 2 to the power of x is an exponential function. This is an exponential function that's been shifted to the right by 2. It's been stretched vertically. It's been moved upwards by 5. I know that if I take a one-to-one function and move it around and stretch it, it's going to stay a one-to-one function, so it should have an inverse. And in fact, we know what kind of inverse it should involve. Since this function involves 2 to the power of something, then my inverse should involve a log base 2. As far as the how do I find my inverse, it's going to be the same steps as before, where first I'm going to rewrite this as y equals instead of f of x equals. And then the second step was to switch our x's and y's. So it's going to be written as x equals 3 times y to the power 3 times 2 to the power of y minus 2 plus 5. And now the goal is for us to now solve for y. And once we solve for y, we'll know what the inverse function is. So first thing I'm going to do, I guess, is get to the point where I've isolated my exponential function. So I'm going to start by moving the 5 to the other side. And then I'll divide by 3. And now I can see that I have just one single exponential function equal to some sort of an output. And I know that if I wanted to rewrite this as a logarithm, since on the right side I have a single exponential function with base 2, then I can rewrite it as a single logarithm with base 2, and I'm going to be switching my inputs and my outputs. Instead of x minus 5 over 3 is my output, it's now going to be the input for my logarithm. And instead of y minus 2 being the input for my exponential function, y minus 2 will be the output for my logarithm. And now I'm almost done. I just need to move the 2 to the other side. So I have log base 2 of x minus 5 over 2 and plus 2. And now that I've solved for y, I can say that that must be f inverse. Oop, I just made a mistake. I realized my 3, I rewrote it down here as a 2, so I'm just going to fix that. There we go. Good thing I caught that. And there we go. So one thing to notice, again, is it's the same steps as before, even though we're dealing with a different kind of a function, even though we're dealing with exponential functions rather than cubes and cube roots, the steps for finding the inverse is really the same. Write it as y equals, switch our x's and y's, then solve for y after. And as part of the solving for y, the key step is taking our exponential function and rewriting it as a log. We're also going to see that the same sort of thing would work if we had a function like this, a log function that I wanted to rewrite with as an inverse. I know for the fact that this is log base 10 because you can see that there's no base written there. So I have g of x as log 3x minus 7 minus 2. So that really is log base 10 of 3x minus 7. And I'm going to find my inverse the same way as before. I'm going to first write it as y equals. I'm going to switch my x's and y's and then solve. One thing I know, though, before I get into the solving and the switching, since this function is a log base 10, then that means my inverse will be an exponential function, base 10. So I know g inverse of x will involve a 10 to a power somewhere in there. So let's do the switching and solving. We have x equals log of 3y minus 7 minus 2. And same thing as before, I'm going to isolate the log first before I start rewriting it as something exponential. So I'm going to move the 2 to the other side. And now I can say that, good, I've got a log by itself on the right side. So now that I have a single log with base 10, then I can rewrite that right side as an exponential function base 10, swapping my inputs and my outputs. So instead of x plus 2 being the output for a log, x plus 2 becomes the input for my exponential function. And instead of 3y minus 7 being the input for my log, 3y minus 7 becomes the output for my exponential function. And now just a little bit of extra work to solve for y, so I will bring the 7 on over to the other side, and then divide the whole thing by 3. And so now I can say that what I've just found should be g inverse of x. So g inverse should be 10 to the power of x plus 2 plus 7 all over 3.